When a medical trainee learns to immobilize complex fractures, what do they use? Too often, it is simple plastic tubes. But the human arm is not a simple plastic tube. It's a complex and multi-layer system of bone, skin, and muscle. These products are not sufficient to train the future generation of doctors. That's where we come in.
Hi, my name is Dr. Hasnain. I've been a doctor for 20 years and I work in primary care. So if a cast isn't applied correctly, a number of problems can occur. Ultimately, this could lead to a clot and it could kill you. Some complications occur quite soon after you put the cast on, and some can occur after a day or so. Well, when you're training to put a cast on, it's still taught in a very old-fashioned way, which is through touch and feel. You don't have any specific metric. You would expect to have a high rate of complications, but I think complications can occur at any stage.
Our project tackles two major problems in medical training. The current standard, the Coles Fracture Trainer, is a static plastic model that costs around £2,000. In short, it teaches technique, but not feel.
So I think the first thing I would say, if they could be taught how to apply the cast in a way that is objective, and that will therefore make it much safer, reduce the complication rate very significantly. It'll also build confidence and competence.
This is exactly what we built. Our team has developed a high-fidelity, intelligent simulator with 5 integrated systems. I, Hisham, built the anatomical core. Michael engineered the circulation, Bogdan integrated the sensors, Bartosz developed the haptics, and Yuvraj designed the UI. My name is Hisham. I built the high-fidelity foundation to this project. To simulate a complex system, you must first build a realistic one. It starts with the skeleton. We modeled a specific anatomically correct arm with every bone from the humerus to the hand at 1:1 scale. This fidelity is a functional requirement, not just a visual nicety. It ensures that when a trainee palpates for the fracture, their fingers are touching the exact landmarks in the right places. And the skeleton isn't just rigid. To achieve lifelike motion, the complex wrist joints are 3D printed from flexible TPU. This simulates the ligaments and allows the multi-axis flex that a professional would expect. Now, material selection must be evidence-based. Our PLA prototype is simply too brittle for the final product. A study in Materials 1 highlights that PLA, while rigid, has poor impact resistance and can fail under casting pressure. PETG provides the high durability of ABS without the manufacturing issues like warping or toxic fumes. It's the clear engineering choice for a robust simulator, but a skeleton is just the start. The realistic feel comes from the soft tissue. A real aim is a complex layer of soft skin and dense muscles. We're simulating with a layered dual durometer system. Since physical testing of silicons is resource intensive, we based our selection in established research. A paper from IEEE, Transactions on Haptics, confirmed that multi-layer models significantly improve perceived realism. Based on this, we specified EcoFlex 0030 for the outer skin. Its gel-like hardness simulates the fleshy feel of the epidermis. Beneath this, the firmer 30A Dragon Skin 30 provides the dense elastic resistance of muscle, critical for palpating the bone. So we have an accurate skeleton, flexible joints, and research-backed soft tissue. But this model serves one final official purpose. It's the chassis for all our integrated technology. My design incorporates the internal architecture, the channels, mounts, and cavities to house all the other systems. The bones are hollowed for haptic motors, the muscle layer embeds the sensor network, and the entire arm is channeled for the blood flow tubing. This core unifies our project into one responsive patient. Michael will explain how we're making the pulse a reality with the blood flow pumping system.
Our project is built on a realistic pulsatile flow system inspired by Stanford University research. We have transformed this concept into an intelligent training platform for managing wrist fracture safely. At its heart, a Raspberry Pi acts as the brain, handling data collection and the custom algorithm. It commands an ESP32 microcontroller, which runs a custom firmware. This ESP32 drives a centrifugal pump, chosen for its durability and fast responsiveness, pushing fluid and rhythmic pulse that feels like a real human heartbeat. Fluid from the IV bag passes through the tubing and a regulator, which simulates vascular resistance. Finally, reaching our 3D printed wrist model. Inside the wrist are pressure sensors monitor the internal fluid pressure in real time. This pressure directly reflects how tightly the cast is being applied. If a cast becomes too tight, the system reacts instantly. The fluid pressure spikes and our trainees feel the pulse weaken or disappear. This gives them direct physical feedback on what restricted blood feels like, teaching them how to avoid compartment syndrome, tissue necrosis, and sore. Meanwhile, the Raspberry Pi collects the sensor's data and uses custom algorithm to recognize unsafe pressure set pattern and assess the performances of the student. It's a responsive, intelligent platform that mimics life.
The key to achieving more realistic experience is a detailed sensory system. We are using a multitude of different sensors to approximate the sensations of pain and discomfort a real person would experience during the procedure. In the heart of our system is a bone displacement sensor. It utilizes a Hall effect sensor and a magnet to pinpoint the position and orientation of the fractured bone piece and to detect any of its movement. This information could then be used for aligning the bone and to simulate pain. In addition to that, the areas near the fracture usually get very sensitive to pressure. In order to detect that, an array of force-sensitive resistors is placed under the skin of the arm. Lastly, as curing of the plaster generates considerable amount of heat, it is important to keep an eye on the skin temperature. This is why thermal sensors are embedded in the skin to sense any temperature differences and to ensure that the skin isn't burned. All this information is then passed to our main controller, where it is used to calculate the pain levels and give feedback to the user.
My name is Bartosz, and I'm responsible for haptic feedback. My job is to take all the data from Bogdan's network and turn it into something the trainee can physically feel. We're using these actuators to create a haptic guidance system. It's simple. If you're far from the correct immobilization, there's no signal. As your hands get closer to the correct position, the frequency and intensity will increase. Once you apply the right force in the right direction, a clear, steady pulse confirmed. It's kind of like a red light, green light system that provides intuitive real-time correction. Finally, we are integrating with the other systems to create a fully immersive experience. We're using the blood flow system to circulate gently warm fluid to the fracture site. This allows the trainee to feel the hotspot of inflammation, a key diagnostic sign. We're also linking to the sensor network. When the sensors detect that the trainee is applying too much pressure, the haptic system will fire a sharp pain vibration. This teaches them the limits of patient comfort. This combination can be adjusted in the software, which UVerge is working on.
My part of the project is a user interface. It guides the user through each step, showing them live safety feedback and then produces a clear report at the end. The aim is that the user will always know what to do next, whether the cast is safe and exactly what they need to do to improve their next attempt. The UI follows a simple 3-stage flow, a guided mode, an assessment mode, and then a report. In guided mode, the user gets prompts and hints for each step so they can focus on learning the sequence. In assessment mode, most of those hints, as well as vibrotactile actuation, are removed, so they have to perform the cast more independently. Throughout the interface, we avoid relying on color alone. Green, amber, and red are states that are always shown with both color and clear text or icons. We use high contrast visuals so that the UI is readable and accessible for all users. During casting, the user will see a step list and a progress bar on the left, and one clear instruction for the center. A small sensor panel on the right showing their alignment and their contrast status using the red, amber, and green after the attempt. We switch to a report screen with the overall score, the checklist, and the rating. A small timeline of any warning and unsafe moments. We include a short pre-quiz and post-quiz to show how much the users improved after the training with the device. This lets us show whether we are actually reducing errors and resits.
The commercial opportunity is huge. The trauma fixation market is worth $9.11 billion today, and is projected to nearly double by 2032.
In terms of the application of this, every single department in the world, this is a global issue, every department in the world where people are attending with broken bones, so every emergency department where fiberglass casts are being applied, every single person in there technically needs training on how to apply it properly. Every single emergency department, each of those requires someone who's competent in being able to cast.
A key part of our commercial case is our hybrid IP strategy. The Stanford Papers license covers only their code, not factual data. And while the Python program is open source, our performance measuring algorithms will be proprietary. Secondly, while patents do exist for general force feedback simulators, they do not apply because our method is novel. Those patents cover basic stress sensors. Our invention is the specific system of using a pulsatile flow loop to act as both the pulse and the sensor. Our innovation, the fracture reduction trainer and algorithm, will be patented, while the Python software will be open source with advanced features licensed commercially to retain control. In short, our simulator makes medical training cheaper, smarter, and safer. We're not just building a product, we're building a living, learning system that adapts to every user, reduces patient risk, and makes world-class medical education accessible to everyone.